Okay, good morning. Let's get started. So far we have discussed about the rate monotonic scheduling and the schedulability criterion. Given a set of tasks, how do you know that the task set is schedulable? And then we had looked at few properties of rate monotonic algorithm, and yesterday towards the end we were discussing about implementation of the rate monotonic scheduling. So today let us start from that point onwards, and towards the end of the last lecture we are looking at harmonically related set of tasks. So let us start from that point. So we are saying that we call a set of periodic tasks as harmonically related if for every task Ti and Tk, if as long as the period of the task Ti is greater than Pk, then Pi will be an integral multiple of Pk. So, wherever the period of a task is greater than the period of another task, then the period will be an integral multiple. So, this is a harmonically related set of tasks. The periods are 10, 20 and 60. So, 20 is a multiple of 10 and 60 is a multiple of both 20 and 10. Now, for a set of harmonically related tasks, the schedulability criterion is that the sum of utilization due to the tasks is less than 1. So, even 100% utilization is possible even if there are large number of harmonically related set of tasks. It is not very hard to show that the utilization achievable is 100%. Let us just review the completion time theorem. So, we were testing the schedulability of a task set by checking whether the expression, this expression holds for every task Ti. Now, for a harmonically related set of tasks, the ceiling can be removed, because whenever the period is larger than another period, it is a integral multiple. So, the ceiling has not required here, the ceiling can be removed. So, if we remove the ceiling, then we get Ei by Pi. From this expression we get Ei by Pi plus sigma k equal to I minus 1 Ek by Pk is less than equal to 1. So, we have arranged the set of tasks in increasing order of their periods. So, the first task I equal to 1 is the task which is having k equal to 1. When k equal to 1, the task has the lowest period or the highest frequency, and we are checking for the ith task. So, for the ith task, we need to check whether Ei by Pi plus sigma k equal to 1 to I minus 1 Ek by Pk is less than equal to 1, or we, since the ceiling is removed, we can bring this inside and we can just change the limits here. We can write I equal to 1 to n Ei by Pi is less than equal to 1. Does that appear okay? Should have been k equal to 1 to I, is not it? But what we have written is I equal to 1 to n. This is for the task Tn, the last task, and we do not have to check this for every task, is not it? What do you think? Is this enough, or is this check enough, or we need to check this expression for every task? So, for the n minus 1th task, we need to check I equal to 1 to n minus 1 Ei by Pi is less than 1. For n minus 2, we have to check I equal to 1 to n minus 2 Ei by Pi is less than 1. What do you think? Should we check for all tasks? Not necessary, because those are part of this expression, isn't it? As long as this holds, all those will hold, because this utilization also includes the utilization of the later tasks, the nth task, n minus 1 task, and so on. So, check here that the schedulability condition from the completion time theorem just reduces to the utilization due to all the tasks is less than 1. So, even if we have a large number of tasks which are harmonically related, we can have even 100% utilization. Now, let us look at a variation of the rate monotonic algorithm, which is the deadline monotonic algorithm. The rate monotonic algorithm, so far we have been telling that it is the optimal scheduling algorithm, but we had made some assumptions. It is optimal scheduling as long as the period and deadline are the same, but when the task deadline and the periods are different, rate monotonic analysis algorithm is not really an optimal algorithm. The deadline monotonic algorithm is actually the optimal one. As I was saying that the deadline monotonic algorithm is based on the rate monotonic algorithm. Here we do not assign priorities based on the task frequencies. Here we assign priorities based on the task deadlines, that is the only difference. Otherwise, rest everything is similar. Now, let us see some properties of the deadline monotonic algorithm, how we check schedulability and so on, and then we will make few comments in this. So, when do the rate monotonic, see here deadline monotonic algorithm, based on the task deadlines, the priorities are allocated. Here based on the rate or the frequency, the priorities are allocated. So, when should they produce identical schedules? What do you think? Yeah, of course. So, when Pi equal to Di, they are actually the same algorithm. So, whenever the deadline is the same as the period, both are identical algorithms and produce identical schedules. But when the deadlines are arbitrary, it is possible that the deadline monotonic algorithm can produce a feasible schedule when the rate monotonic algorithm fails. But the rate monotonic algorithm will always fail if the deadline monotonic algorithm fails. Please construct an example where the deadline monotonic algorithm produces a feasible schedule when the rate monotonic algorithm fails.
Is DMA static algorithm?
Of course, everything else is similar. See, it is also a static algorithm. Everything else is similar to the rate monotonic algorithm. It is a static priority algorithm, but only thing is the priority is assigned based on the deadline rather than the rate.
Previously, you have said that RMA is optimal static algorithm. So, when RMA fails, then all others should also fail.
No, that is what I have been trying to tell, that to start with we had told it in very simple words that rate monotonic algorithm is optimal algorithm. What we left unsaid is that when the deadline and the period are the same, it is the optimal algorithm. That we left it unsaid just for simplicity, but now we are slightly making it more complicated. We are saying that, see, there possibility that there are some tasks which might have their deadlines and periods different. Normally, we will see that for a large set of tasks, the deadline is the same as the period, but it is possible that for few tasks, deadline can be different from the period. So, for that, rate monotonic algorithm is no more optimal. So, here we are saying that it is possible that deadline monotonic algorithm can produce a feasible schedule when the rate monotonic algorithm fails to provide a schedule. It is not difficult to construct an example, but please construct an example for this. We will not really wait for this one, we will just leave you as a work. It is very simple to do it.
If deadlines are less than the period, then probably that will be the case.
No, deadlines are less than period, but still rate monotonic might produce a feasible schedule, isn't it?
Yeah, but
so just so that something which is where the deadlines will not be met using rate monotonic, but it will be possible to meet them using deadline monotonic. But the rate monotonic will always fail if the deadline monotonic fails. So, let us just check this set of tasks. Let us say the task 1 execution time is 10 millisecond, period is 50 millisecond and the deadline is 35. E2 is 15 execution time, period is 10 millisecond and deadline is 20 millisecond, and for E3 the period and the deadline are the same. So, let us check the schedulability of the task set under RMA fast. Please try that. Find the utilization for task 1, which will be 10 by 50, isn't it? Okay, so let us not wait for your answer, because those who have already done, they can cross check the answer. To check the Liu-Layland, we find that the utilization is greater than 1. But let us do the completion time check for the deadline monotonic algorithm. See here implicitly, see for even for applying RMA, we have taken that the 10 must be completed within 35, 15 must be completed by 20 and so on. So, here see here one thing is, according to the rate monotonic algorithm, T1 has higher priority compared to T2, isn't it, because of their periods. But according to the deadline monotonic algorithm, T2 has higher priority than T1, isn't it? So, possibly that makes the difference. And we are checking whether T2 will meet its first deadline. So, 15 is the execution time and deadline is 20 and it meets it. For T1, which is the next priority, that is the second highest priority, 15 plus 20 is 35, it will just meet, and for T3 both T1 and T2 will have to consider their occurrences. See here, the occurrences have to be with respect to the period, isn't it? Implicitly in the calculation we have used that. How many times they occur is based on their period, not on the deadline. See here, this is 20 is the deadline, but actual period is 200, isn't it? No, 100. Actual period is 100. So, the deadline is 20, but the actual period is 100. So, we have used those to compute this and we find that 90 is less than 200. So, all the 3 tasks will meet their first deadlines and it will be PI. No, see, we are trying to find out how many times the task will occur in that interval, and whenever it occurs, it will start executing the higher priority tasks.
EI by DI, sigma EI by DI.
Here we have checked EI by DI, yes.
It should be EI by PI.
No, see, if we can check EI by P, okay, here you are saying this should be DI, is it? Okay, so minimum of PI and DI, minimum of PI and DI. Okay, here we should have made this correction. So, the task set is unschedulable by the rate monotonic, but it is schedulable under deadline monotonic. But just one question, that why do then people use rate monotonic in programming and not deadline monotonic? As we are saying that majority of the schedulers are rate monotonic schedulers, not deadline monotonic schedulers. So, what do you think?
Deadline may be difficult to anticipate.
No, deadline can be found out. For every task, deadline can be found out.
Relative deadline may be difficult.
Probably because of in real time systems both deadline and periods are same.
Yeah, okay. So, in most of the situations, vast majority of the tasks, the deadline and the period are the same. It is very unusual to find tasks for which the deadline and period are different, and for that we need to tailor the rate monotonic algorithm to handle those issues rather than trying to use the deadline monotonic algorithm.
What if we use the DMA itself, then if P and D are equal, it will behave like RMA only.
Okay. So, what he says is that the deadline monotonic, if the rate and the period and the deadline are the same, it is actually the RMA. But the thing is that DMA is much more complex to understand and implement. So, can you please try to investigate what is the complexity in implementing the deadline monotonic algorithm, what is the complexity, and please investigate if there are any other reasons why DMA is not as popular as rate monotonic algorithm. Whenever you talk to a real time programmers, if you ask him that what is the algorithm you are using, he will say using rate monotonic algorithm. So, why this situation? Please investigate and submit me a report if you find something important or significant. Okay, let us proceed.
And what is the difference between earliest deadline first and DMA?
Okay, so there is a question here that how is earliest deadline first and deadline monotonic algorithm different?
Yes, deadline first is a dynamic. We keep on changing
Yes.
schedule.
Yeah. So, earliest deadline first, as he says that at each instant, at each scheduling point, you find the nearest deadline and that is taken up for execution at each instant or each scheduling point. At each scheduling point, the scheduler determines which is the task having the nearest deadline and then takes it up. Whereas, in a deadline monotonic algorithm, you just find the relative deadlines of all the tasks beforehand, not at every instant, and then find out, assign priorities based on that. So, here the priority does not change in a deadline monotonic algorithm, whereas EDF depending on at which scheduling point you are talking of, different tasks might be considered higher priority. Is that okay? Okay, let us proceed from that point. So, let us look at few other issues. One is that since the task execution times are very small, most of these tasks complete in few milliseconds and also their periods are also small. So, we should not ignore the context switching time. So far, for simplicity, we have been ignoring the context switching time. So, during the schedulability analysis, we should also consider the overhead due to context switching. We should take the pessimistic, because context switching also takes different times, it is not a constant time actually. So, it might take between a range of values, but we should take the pessimistic value. Now, let us assume that the context switching time at the worst case takes some time. So, we need to consider that, even though so far we have been neglecting that for simplicity. Now, let us say when does the context switch occur? One is that when it preempts the currently running task. So, higher priority task which has arisen, which has come in, will preempt the lower priority task, or if the CPU is idle, there will be no preemption, the task will start running. But for both these cases, there will be a context switch. Does not matter whether it preempted or it did not preempt, the CPU was idle. For both these cases, the context need to be loaded, is not it? The context switching has to occur. So, if you consider that, in the worst case, each task incurs at most 2 context switches. See, here we will have to consider the worst case scenario, not the average case or the best case, because we want to guarantee that the tasks will be schedulable under the worst situation. Unlike in our normal traditional operating systems, where we are more concerned about the average case behavior, here we are concerned about the worst case behavior, and at the worst case each task incurs at most 2 context switches when it preempts the currently running task and when it completes. But what if a task is before it could complete, it is preempted again? I mean, it is preempted, and then once it starts running again, it is preempted by some other task, again it starts running and again preempted. So, is this assumption holding for this? At best,
For every run it should have to.
no, just look at the question. I am saying that irrespective of how many times a task has been preempted, at most we can consider that it has undergone 2 context switches. Every task has undergone 2 context switches. Is that assumption valid?
Need not be, sir. Because as and when higher priority processes come, then it has to, the need may arise that it has to get preempted more than 2 number of times.
No, suppose see, we are trying to consider how many times the preemption we need to consider for every task.
So at least once.
At least one.
Because some.
No, not at least, at most.
At most twice. So because if it has been preempted by some other task, then
Yes.
that will be a higher priority.
Exactly.
So that will complete fully.
Yes.
So that will take.
Exactly. So, let us see his answer. Let us look at the diagram here. See here. So, a higher priority task has come in here, and this has 2 context switches taken care here, right. 2 context, one is, see, this task started coming in here at this point, there was a 1 context switch. Now, next time this task has preempted it, and this context switch will be counted towards it, and which will be in our expression taken care, because it is a higher priority task, and then it started running again, right. So, the higher priority task has undergone 2 context switches, and this had undergone 1 context switch at this point, and now after it completes there is 1 more context switch. So, just think about it, that at most every task incurs 2 context switches. If we develop our expression by that every task incurs at most 2 context switches, we will be doing all right, because the higher priority task context switches will be taken care of, right. They will be added to the lower priority tasks completion time. So, let us see the expression, possibly that will make more sense. Let us assume that the worst case context switching time is equal to c millisecond. Now, if we consider the overhead due to context switching, in effect we can say that the execution time of every task increases by 2 context switches, because at most 2 context switches are involved for every task. So, the execution time, instead of E I, if we make it E I plus 2 into C, we should have taken the overhead due to context switching. So, let us use that concept here. we have 3 periodic tasks whose execution time is 10 millisecond and the period equal to deadline is 50 millisecond. For E2 it is 25 millisecond and 150 millisecond, and for T3 it is 50 millisecond and 200 millisecond, and the context switching time is 1 millisecond. See, 1 millisecond is very comparable to 10 millisecond, 25 millisecond, 50 millisecond. So, if we ignore it, the context switch time here, we may not be doing all right. We might arrive at a decision about schedulability which can turn out to be wrong, because the context switching time is comparable to the task execution times. Now, let us see how we need to determine whether the task set is schedulable. So, what we need to do? Can you please tell what we need to do?
We need to increase the execution time to 10 plus 2c.
Exactly. For each of the task, we need to increase it by 2. So, this will become 12, this will become 27 and this will become 50. Now, when we apply the completion time theorem, we will see that for this to complete, the first task to complete it is 12 is less than 50. For the second task to complete, it will be 27 plus 3 into 12. See here, the context switch times are taken care, the number of times it was interrupted. Those context switches are taken care by the higher priority task. We are factoring here those context switches. So, considering just 2 for this is all right. Similarly, for this task, we will factor in the context switches due to this T2 and T1. Now, let us see the solution. So, the execution times for each task becomes 12, 27 and 52 as we were saying, and 12 is less than 50. So, the first task satisfies the completion time theorem. Task T2, 27 plus 12 into 3, this also satisfies, and the third task also satisfies the completion time theorem. So, even after factoring in the context switch times, the task set is schedulable. Does that appear all right? Any difficulties here? Okay.
We always assume the context switch time to be constant.
Yeah, see, we are taking the worst case scenario. So, if we say that a task set is schedulable, under all situations the task set should be schedulable. That is why we are taking the worst case context switch time. Okay, let us proceed. Now, let us consider self suspension. This is another issue which we have so far been ignoring. A task, when it starts running, the execution time is given, we have been assuming that it runs to completion, but it might self suspend. Even though it is the highest priority, still it might relinquish the CPU and suspend itself. Why is that so? What do you think? Yeah, exactly. A task might self suspend waiting for IO or maybe some events. So, those are two conditions under which a task might self suspend. So, let us look at that the task, when it performs input output operations or it is waiting for some events to occur, it self suspends. Now, what is the impact of self suspension on the schedulability? We need to analyze that, because if a task self suspends and runs at later instant, it can affect the schedulability of the lower priority tasks, is not it? It will not affect the schedulability of higher priority task, because it has to anyway yield the CPU to higher priority tasks, but lower priority tasks might be affected. So, let us see what is the impact. Again, we will make a simplistic assumption here, we will restrict the number of self suspensions. Okay. So, we have so far restricted to considering only 2 scheduling points, is not it? What were the 2 scheduling points?
frame starting.
No, these are event driven schedulers. See, what you are talking of is cyclic schedulers.
Event completion. And
Yeah. So, in event driven scheduler, so far we have been considering two scheduling points. One is when a task arrives, the scheduler need to check whether it is a higher priority task than the currently running one and whether it should be scheduled. And the second is when a task completes, it will check which is the highest priority now and take that up for execution. So, two scheduling points we have so far considered for event driven scheduling. Now, we have to consider a third scheduling point, which is at the self suspension. When a task self suspends itself, it is placed on the blocked queue, removed from the ready queue and placed in the blocked queue. From a traditional operating system, we know this much. And out of those tasks which are in the ready queue, it dispatches the next highest priority task. So, in addition to task completion and task arrival events, we also need to consider the self suspension events. And let us assume that every task undergoes at most a single self suspension. We will have to restrict it to a single suspension or two suspension or something like that, because if it suspends arbitrary number of times, doing a schedulability analysis will become extremely difficult. So, let us denote these two delays. One is the delay the task Ti incurs by its own self suspension, and also that of its all higher priority task, we will denote it by Bti, and Bi is the worst case self suspension time of the task Ti. So, Bi is the self suspension time of the task Ti, and Bti is the self suspension, is the delay that the task incurs due to its own self suspension, which should include Bi, and also the effect due to the self suspension of all higher priority tasks. Right, we are implicitly assuming here that the tasks are arranged in order of their periods. So, we have written this expression that Bti, the worst case delay that the task Ti will incur, is its own self suspension, which is obvious that its completion will be delayed by the time it self suspends itself, right. And now, just look at the second expression. We are saying that for the higher priority tasks, it is the minimum of the task's execution time and the self suspension time. So, what about this one, the second term? Shouldn't we have written just a summation of Bk? What do you think? Anybody would like to comment on this? Is the question clear? See, for the first term in the delay due to self suspension, which is Bi, is obvious, because if a task has suspended for some time, its completion time will be delayed by that much. But for the higher priority tasks, when they self suspend, we are saying that we need to consider the maximum, the execution time and the self suspension time. Sorry, minimum of the, sorry.
The effect of the higher priority process will only incur in terms of this delay only to the lower. They will not affect lower priority process in any other terms. In terms of delay.
Not clear. Anybody would like to answer any other way? Yes, anybody like to comment on this? That why is it that we are considering the minimum of the self suspension time and execution time of the higher priority task? Okay, the answer is not so complicated. See here, a lower priority task Ti gets delayed due to a higher priority task when after a higher priority task self suspends and it blocks the execution of the lower priority task, right. Now, even if it self suspends for arbitrary number of point of time, the maximum overlap that can occur is Ek or Bk, right. See, if it is self suspended and by Bk the task has got delayed. So, the maximum time on which it will overlap on the execution of the lower priority task is minimum of Ek and Bk. So, even if it is squarely overlapping on the lower priority task, it will delay it by maximum Ek, right. Now, the delay is also restricted by Bk. If Bk is smaller, then due to the self suspension it will at best overlap for Bk, is not it. From the earlier case where there was no self suspension, and when the self suspension occurs for a higher priority task, the maximum change in the overlap will be Bk. If Bk is smaller, or Ek is the, if Ek is smaller, that is the maximum overlap that can occur. So, the maximum delay that a lower priority task will incur due to self suspension is its own self suspension and minimum of Ek Bk for all higher priority task for single suspension. Sorry,
It's not clear.
Not
So
clear.
We are considering Ek.
okay. See, a lower priority task gets delayed due to self suspension when there is a higher priority task which has become after self suspension ready or something like that, right. So, the higher priority task will be taken up and this will not be executed. Now, if let us assume the case when Bk is less than Ek, right. So, what will be the maximum overlap that will occur with the lower priority task? Bk. Now, let us say Ek is less than Bk. So, even if it has delayed it by Bk, but the maximum overlap that will occur is Ek, is not it, because it will complete by Ek, it will can prevent the lower priority task from executing by maximum Ek, is not it. Even if it has self suspended for large number of time, the maximum overlap due to this task will be Ek, because after Ek it will anyway complete.
But Ek should be the execution time of the lower priority task, not the completion time of the
No,
task
Ek
which
is a
self-suspended.
no, Ek is the higher priority task which is blocking a lower priority task Ti. So, Ek when it is executing, Ti will not be able to execute. When Tk is executing, Ti will not be able to execute, and it will complete in any way by Ek, right. Ek is the execution time. So, the maximum it can delay is by Ek, but when Bk is less than Ek, it can at most delay it by Bk, right. Just think over it.
When Bk is less, that is obvious. Sir.
Yes.
But when Ek is less, even then the task Ti may not get executed in between the waiting of this other high priority.
No, once it says self suspends, the CPU is relinquished, any task will start executing.
Yes, but still the waiting delay time we have to consider as the complete BM.
No, see Bk it has waited, the higher priority task self suspended itself, and that time the CPU is available. So, that is not a problem. The problem is that when it self suspends and then starts executing in phase, or when the lower priority task is executing and it preempts it, is not it. So, that we are saying is that it can at best prevent the lower priority task from executing by maximum Ek time, because by Ek time the Tk will complete. Think of it. So, the maximum delay due to self suspension is Bti, which has two components, one is its own self suspension and the other is minimum of Ek Bk for every higher priority task, that is k equal to 1 to I minus 1. Now, we need to change the Lehoczky's completion time theorem as follows. So, earlier we were just writing Ei sigma k equal to 1 to I minus 1 ceiling of Pi by Pk into Ek. Now, we need to add this term BTI, because this time will also be, the task will be delayed, right. And of course, this is a single self suspension that we have considered. If we consider 2 self suspensions or so, or maximum n self suspensions, we need to change this expression here. So, let us look at this exercise. We have 3 tasks T1, T2, T3. For simplicity, I mean without making it too non-trivial 2 tasks, we are just considering 3 tasks, but in a realistic scenario we might have 5 or 10 tasks. So, E1 is 10 millisecond and P1 is 50 millisecond, E2 is 25 and 150, and E3 is 50 and 200 millisecond. And the 3 tasks have different self suspension, maximum self suspension times. For T1 it is 3 millisecond, for T2 it is 3 millisecond, and for T3 it is 5 millisecond. So, will this task be schedulable? What do we have to do here?
Calculate BT for each and every task and then add it to each.
Exactly. So, we need to compute the BTI for every task Ti, and then in the completion time theorem we need to factor in that delay. So, that is what is done here. For the first task it is 3, BTI is 3, and the delay due to higher priority tasks is 0, because it is the highest priority task. So, execution time is 10 and its self suspension is 3, which satisfies is less than 50 its deadline. T1 will meet its deadline, but T2 we need to consider the higher priority task, which is 3 plus 3 is 6, and ceiling of 150 by 50 is 3. So, 3 into 10 is 30, 55 plus 6 is 61, which is less than 150. So, T2 will also meet its deadline. For the task T3, we need to add its execution time, and then the self suspension time or the execution time, whichever is lower for all higher priority tasks, and then the execution time for the higher priority tasks during this duration. So, if you simplify this, that is 2 into 25 plus 4 into 10 plus 12 plus, that is 50, is not it? So, that is 50 plus 12 plus 40. So, 102 plus 50 is 152. So, for T3 also it will meet the first deadline. Now, let us see how do we take care of both self suspension and context switch. So far we have been assuming that the context switch is restricted to 2, one when it preempts or it starts executing, and another it completes. And we said that all higher priority tasks, when they preempt, it will be factored in and we do not have to consider for them. So, just 2 was enough, but when we have additional scheduling point due to self suspension, we need to change that calculation, the maximum number of context switches that we need to take into account. So, let us look into that. Since we are assuming a single self suspension, the self suspension will introduce at most 2 other context switches. So, we need to make it EI plus 4 into C.
Suspension and some resumption.
Yes, self suspension and resumption. So, for taking care of both self suspension, single or 2 times self suspension and context switches, we can do it very easily. But now, let us see another issue in using the rate monotonic algorithm in actual system development. You will have situations when the task criticality is different from the task priority. See, here we have assigned priority solely based on what is the rate at which the tasks are arising, right, the rate of the task, based solely on that criterion I have assigned the priority, and it might so happen that a task which whose period is slightly larger, but that is a critical task. For example, the response needed for a robo to take a deviation from an obstacle. Now, but that task should not fail even when there is overload. A lower priority task, it can fail and still the system will work, but for critical tasks in the overload situation also it should not fail. So, how do we take care? Because here we have a contradiction, a conflicting situation here, where a lower criticality task has higher priority. One thing is that we can raise the priority of a critical task, even if we find that its period is high or the rate is low, still we can assign it a priority of 1. But if we do that, then we will be violating the schedulability assumptions in the schedulability criterion computation, right. So, the schedulability results will not be applicable. Now, what if we so what is the solution? How do we do that? A solution was proposed by Shah and Rajkumar, the period transformation technique reported in 1989. Now, let us see the essence of the result, very simple result actually. The paper is available on the internet. If you just give Shah and Rajkumar period transformation technique, you will get the paper. So, here the task Ti has execution time Ei, and let us say it needs to complete by Pi, let us say. So, what we can do is we can say that, see, we will split it into k smaller tasks. So, instead of considering Ei over a period Pi, we can as well consider Ei by k over Pik. That will take care of it, is not it? We just reduce the task Ei Pi to Ei by k and Pi by k. So, its in effect its period has reduced by k times, and this is done at a conceptual level. We do not have to really split the task. In the schedulability computation we just use this. But one thing we must note here, that okay, that we will just talk little later. So, let us just look at an example of the application of the period transformation. So, let us consider two tasks. E1 is equal to 5 millisecond and the period is 20 millisecond, and E2 is 8 millisecond and the period is 30 millisecond. And then we find that T2 is a critical task, whereas T1 is not as critical as T2. So, if T1 misses the deadline, it is not a severe failure, but T2 should not miss its deadline, then the robot tumbles or something like that, collides and tumbles. So, this is a critical task. So, what we have done here is that we have transformed T2 into T2a. E2a is 4 and P2 is 15. So, we have in effect split the execution time and the period by half, and now see that T2a is assigned a higher priority than T1, and we can also use this in our schedulability analysis. But just one observation here, I think I forgot to write here that see, even though we are splitting it on the into k smaller tasks, the actual deadline is on the last task, isn't it? The last of these smaller tasks is actually critical. So, if we can use that in our schedulability analysis, possibly the schedulability it will become more schedulable, right. We can take that into for the tasks, for the k minus 1 tasks, the deadline if it is also missed, we not a problem, I mean missed by a small factor, it is not a problem. But for the last task, subtask, the deadline is missed, then the task will fail, right, just remember that. But is there any impact on schedulability at all? Is it that a task set which was schedulable earlier, by splitting it, it will become unschedulable, and is it also that we can improve schedulability of a task set by splitting the task into smaller periods? So, we need to analyze two situations. One is that an already schedulable task set, after we split a critical task into smaller parts, it becomes schedulable, and the second is, can we improve the schedulability of a task set which was unschedulable earlier, and by splitting it we have improved its schedulability, it has now become schedulable. So, both ways we have to consider. Please investigate this. As I was saying that Raj Kumar's paper is available on the net for everyone to look at it, 1989 paper. You can consult that or any other paper or any other literature that you wish, and please submit this result that what is the effect of period transformation technique on task schedulability. So far we have been posing large number of bonus problem, please attempt that seriously, because we will evaluate all of them, and whoever is sincere trying to put some effort and do it, search the literature, Google search and think about it originally and submit results, will be rewarded. So, let us break now, we will meet for the next lecture.